Okay, so today we're talking about 7.3 sample means. This lays the foundation for a lot of second semester stuff here. So let's get into it. So we call this title be sampling distributions of X bar, or of the sample mean. Sample X bar means we're talking about the sample. So this is, this is actually similar to the activity we did about the age of pennies, right? We took sample sizes of 5 and 20, and you notice that, first of all, it's starting to look approximately normal in both of them, but when it was 20, it had a smaller variation there. And so that's just a concept that's nice to know. As n increases, the standard deviation is going to get smaller. In fact, there's a reason for that in the formula. Because the formula is the standard deviation of the population, that's the numerator, the Greek letter is the population parameter, divided by the square root of n, so that how big the sample size is makes a big difference as to what the standard deviation of X bar will be. So whenever you take a sample, you have to remember to do this. And honestly, this is probably the toughest part of the lesson. A lot of students will just use the population standard deviation and try to do the problem, but you have to remember if you're taking a sample with means, you have to use this standard deviation formula to get the answer. It's on your, you don't have to memorize it. It's going to be on your formula sheet. Standard deviation, again, typical deviation from the mean. In order to do that, we need to check the 10%, less than 10% condition. So in this case, well, we don't have any context for this problem, but that's what we would check in order to do the standard deviation. Okay. Be careful on your notation. You might lose credit if you use the wrong label. So if you're not sure, don't put the label, put the answer if you're not sure. The number of movies viewed in the last year by students at a large high school has a mean of 19.3, standard deviation 15.8. Suppose you take a simple random sample of 100 students from the school and calculate the mean number of movies watched. So identify the mean and the sampling, mean of the sampling distribution of X bar. So again, the notation on this is probably important. So the mean of X bar, so the way we say that is, let me get a thing here. Okay, so the mean of X bar is equal to, it just tells us it's 19.3. It's not a bad idea to put context here, so 19.3 movies. Calculate and interpret the standard deviation of X bar. So again, to do this, we have to have a formula. So standard deviation of the population was 15.8. In order to check this condition, we should probably verify that the less than 10%. So 100 students, this is a large high school, so you have to assume it's more than 1,000, is less than 10% of the school. And so we can use that. So the standard deviation of the population was 15.8. So standard deviation of X bar, that's how we write that. That's a subscript there. It's hard to tell, but that's below. And so it's a fraction, right? It's 15.8 is the population standard deviation divided by the square root of n, and I think that was 100. I could divide it by 10, that's essentially 10, so that's 1.58. It should be no surprise that the sample standard deviation is much smaller than the population standard deviation. That's going to happen every time, right? We think it's going to be smaller. The larger n is, the smaller standard deviation is going to get. And so there you go. About 1.58 movies. Again, put the context of that. Always a good idea to do that. We forgot to interpret. Sorry, the question is to calculate and interpret. So interpret, again, remember standard deviation is typical deviation from the mean. So in this case, in a sample of size 100, the sample mean number of viewers would typically vary by about 1.58 movies from the true mean of the number of movies. We haven't described its shape. So we have talked about this with proportions, but means are a little bit different on this. So the first thing you need to know is that if you have a population, that top graph there looks approximately normal, and you take a sample, really of any sample size there, if the population is normal, the sample is going to be approximately normal as well. So if that's true, that works. So sometimes you don't have to do any calculation or proving. Just say the population is approximately normal, which means the sample is going to be approximately normal. this is true no matter the population size. So that's important. So sometimes, every once in a while, that kind of problem comes. You go, okay, we don't have to calculate anything. We don't the large counts condition NP. We can't do NP because we don't know what the proportion is. It's means, and so you can't use that old thing that you used to use. Okay, the heights of young women follow normal distribution with a mean of 64.5 and a standard deviation of 2.5. Find the probability the randomly selected young woman is taller than 66.5. Okay, so in this case, this is just the population here. So we're gonna, because the population, all women, the population of women, follows an approximately normal distribution, then the sample we're taking, in this case we're not taking a sample, but if we are, the sample is going to be the same. It's going to be normal as well. Okay, so if that's true, we could draw this, right? The mean is 64.5. Standard deviation is 2.5. So if you add 2.5 to that, you get 67. Subtract 2.5, you get 62, and so forth. It's 66.5. So 66.5 is here, and you want that or bigger. So you would 66, that's 66.5 there. So you go to your norm CDF on your calculator. So menu 652. Lower bound is 66.5. Upper bound is infinity. I'm just going to type a big number. Mean is 64.5, and standard deviation was, I think, 2.5. So you get 21%, 21.18%. 21.18%, or 0.2118. There you go. That's the work for that one, if you need it. Okay, now let's answer the second question. So find the probability that the mean height of an SRS of 10 young women exceeds 66.5. That almost seems like the same question, doesn't it? I mean, it's kind of silly, like, wait, they're asking the same question here. But they did say that n equals 10. So now we're taking a sample, which we didn't take in the first case. We would not really take a sample, just said what's probably of any person who was selected. Because of this, we have to change our standard deviation. Its population standard deviation was 2.5% or 0.025, I believe, or 2.5 inches, sorry. 2.5 inches, I guess, if I'm paying attention. Okay, so then, so we're going to have to figure out, so get your calculator out, standard deviation of X bar will be the population standard deviation with 2.5 divided by the square root of n, and n was 10 here. So then you get your calculator out and you get that number, right? So probably the mean. So you've got to do that calculation. Before we do that, we should probably check the less than 10% condition. Just look at that here. So the heights of women. So is 10 less than 10% of all young women in the United States? Absolutely, right? So the mean is 64.5. Because it's less than 10%, we can use the formula. And when you type in the calculator, you get 0.79. And so that's also normal, right? So what's the chance that you exceed 66.5? So again, your lower bound, you're going to do norm CDF is 66.5. Upper bound's infinity. And then you plug in your new mean and standard deviation there. You can see the last line is what you would type in your calculator. Lower bound 66.5, upper 1,000, mean, and so forth. This is just taking a bird's eye view of this. So you can see that the standard deviation of the population was 2.5, but the standard deviation of the, it was not that big. It was 2.5 divided by square root of 10, which was 0.79. So 0.79 is a lot smaller than 2.5. This is going to happen. And so you can see just in general, when you take a sampling distribution of X bar, it's always going to have the smaller. So that the taller, thinner one there, That's the sample because it doesn't have as much spread to it. Many students forget to divide by square root of n. So they put the population standard deviation when they take a sample, and that's just going to get you dinged every time. Okay, this is interesting. So in this case, some really weird populations. These are 3 different examples. The first one on the left there, when it's flat across the top, that's called uniform. So even if the population is uniform, if you take samples of size 2 or 25, they start to look more normal. Now 2 doesn't look that normal there. It looks like a triangle kind of, but samples of size 25 starting to look more normal there. If it's right skewed, the second example, that's the population up top, then samples of size 2 will also be right skewed, but samples of size 25, they're starting to look more normal. It's a really weird bimodal data set on the top right there. If you take just samples of size 2, you're going to get trimodal data, I guess. I mean, it's kind of strange looking. But if you take a large enough sample, it's going to start looking more and more approximately normal. This is called the central limit theorem. If n is sufficiently large, the sample size is big enough, then we can say that this thing's approximately normal. Even if the population was bimodal, like that crazy one there, or any skewed right, skewed left, it doesn't matter. If n is sufficiently large, well, what's sufficiently large? Typically, we're going to say n is greater than or equal to 30. So 30 or bigger for n, we're good to go, right? We have an approximately normal situation there, and so it's really nice. Keeps the manager in an auto center based on service records from the past year. The time and hours a technician requires to complete a standard oil change with inspection follows a right skewed distribution with mean of 30 and standard deviation of 20. So that means, like, if you think about that, plus or minus 1 standard deviation. So it might take, 10 minutes. It might take 50 minutes to change your car. You kind of never know, but somewhere in that range there. Typically, if you're 1 standard deviation away. For promotion, Keith randomly selected 40 current customers, offers them a free oil change and inspection if they redeem the offer during the next month. Keith budgets an average of 35 minutes per customer for a technician to complete the work. That seems reasonable. I mean, the average is 30, so 35 is more than average, so that might be enough, but will it be enough in every case? I don't know about that, but it'd be enough in quite a few cases. So the questions that follow this one is this. Calculate the probability the average time it takes to complete the work exceeds 35 minutes. So you want to start with a mean. Mean was given to us, it's 30. Check the less than 10% condition. 40 is less than 10% of all current customers. So you're going to plug into that formula. Standard deviation of the population, which is 20, divided by the square root of n is 3.16 in this case. We can't draw the normal curve until we check the large, it's kind of like the large counts condition, but it's a little different than proportions. We have to make sure the sample size is at least 30. That's our kind of break-even point there. And so because it is, we're going to try it and do norm CDF, and the bottom thing there is going to be the answer from 35 to 1,000 or to 1,000,000 or infinity with a mean of 30 and standard deviation 3.16. Part B says, how much average time per customer should Keith budget if he wants to be certain 99% of that doesn't go over budget? So he doesn't want to go over budget. He really wants to be careful about this. So remember that command, inverse norm? So that's what you're going to do here, is inverse norm. Okay, so let's remember how to do that. So if you haven't done it in a while, menu 653. Area is 0.99. Standard deviation, I think, was given to us was 30, and it was 3.16, I believe, from memory there. Okay, so we get 37.35. So 37.35 or 37.4 minutes. To be 99% sure he's budgeted enough time, he should plan for an average of 37.4. So that would be a better guess. He didn't make a terrible guess there, but That was only about 95% accurate when you did that one. If you want to do these extra problems, you certainly can. There is the problem. There's the answer to that part. Part B, calculate and interpret the standard deviation. Did we take a sample? We did. Don't forget to check the condition and use the proper formula there, and you'll get it. So it varies by about 0.46, or about half a day from the true mean days. So very similar to the other question where the first one's about the population, the second one is about the sample, so we have to change the standard deviation using the formula. There's the work for that, and that's your lesson for today.